Hello and welcome everyone. Very happy that we're all together again. In this tutorial, we will start illustrating the interior thermal load calculations according to the SI system standards, and we will start with the lighting thermal load calculations. So fasten your belt and let's get started. The aim of this tutorial is to know how to calculate the thermal load for the lighting system inside the building, as the lighting loads are some interior elements inside the building spaces, so it's considered to be one of the interior loads as we learned it before. So let's go ahead. First of all, we know that the lighting loads are considered to be some thermal loads. This is because the lamps and the luminaires are producing the light in addition to the heat. So the heat that is produced from the luminaires are considered to be some thermal loads that we need to calculate its value. And we can find that the thermal load of the lamps to be calculated according to this equation. And you can note that this equation is very similar to the equation that we used to calculate the lamp's thermal loads in the IP system, except that we cancelled the factor 3.4, which were used to convert from watt to BTU per hour, as here in the SI system we are working on the watt, not the BTU per hour. So the equation now is the multiplication of those four factors, Q sub I times F sub A times F sub C times the CLF or the cooling load factor. So let's anchor them step by step. As usual, the final thermal load is calculated in watt. Then Q sub I is the amount of power that the lamp consumes, and it's calculated in watt. So let's see how to calculate the amount of power that the lamp consumes, which is calculated in watt as we said. Here this is done by one of two ways. Firstly, if we know the lamp power from its datasheet, we can sum all of the lamp's power to get the final value in watt. And here we have an example at which we have this AutoCAD drawing for a printer room, and this is the electrical layout for its lamp's design. So we can get the datasheet from the electrical designer, as it's not our job now to calculate the electrical design. And for now in our example, we are using two types of LED luminaires, and the power of the first LED luminaire is 20 watt and the power of the second one is 28 watt. So the total luminaire's power now equals 2 times 20 plus 1 times 28, which gives a total luminaire's power of 68 watt. So that's about the first method. Also, we have a second method which we can use in case of we have no data about the lamps used in the building, and this is a more practical case because in many cases we are designing the HVAC system for a new building which is under construction. So at this time there is no lamps design in the building, and for this reason we use a standard table which tells us about the amount of power that each type of places needs in watt per feet square. So in our case, the design is for a printer room, and we find its nature to be nearer to an office. Hence, we select the office enclosed row, and its corresponding lighting density now is 1.1 watt per feet square. Then we need to calculate the area of the office. So the area of this printer room from the architectural plan is 5.5 meters square. But we need to convert the area from meter square to feet square, as the lighting power density is per feet square now. So we multiply 5.8 times 3.28 square, which gives us the area now of 62.39 feet square. After that, we multiply the area by the lighting power density to be 1.1 times 62.3, which gives us a total power of 68.6 watt. So when we multiply those two values, we will have purely the watts of the lamp, which is Q sub I. And you can compare this value with the previous one, which was 68 watt. So they are very near to each other. So the two methods gives approximately nearer results to each other. Now the second factor we need to calculate is F sub A, and this F sub A is the fraction of in-use power, and this factor refers to the number of working lamps or the total number of lamps. For example, the nature of the office we are working on recommends that only 2 lamps of the 3 lamps we have to be turned on at the same time, or 2 luminaires to be energized out of the 3 total luminaires we have, or not all of the lamps will be working at the same time. Here in that case, F sub A will equal 2 over 3, which is 66%. But the standard codes recommends that this factor to be 1 for the design to be on the safe side or to predict the worst designing case. Now the third factor we have is F sub S, and this F sub S is the lamp Pallas factor, and this Pallas factor, as we learned it before, is set to compensate the thermal heat produced from the Pallas of the lamp, especially for the fluorescent lamps, and we have learned it before how to calculate it from this table. So for the fluorescent lamps, we suppose this factor to be about 1.3, but in our example here, as we are having some LED luminaires, so we can select this Pallas factor to be 1.1 for the smaller LED luminaires, and we can set it to be 1.2 for the larger LED luminaires with the larger power. Hence, for our example, we can set this value to be 1.1 as our LED luminaires are some smaller LED luminaires to cope with the smaller printer room we have. Very good. Now the final factor we have is the cooling load factor. And this factor specifies the number of hours that the lamps will work on in the day, and this depends mainly on the nature of the place that we are working on. For example, if we are talking about a hospital reception, at that case the luminaires will be supposed to work all the day, as the hospital is ready anytime for the emergency cases, and for this reason we set this value to P1. While in our case for the office, we suppose that the lamps will work for the working hours only to be about 10 hours only, and here to detect this cooling load factor for the lighting system we are working on, we will get it from this Azure SI table, and the first factor we enter this table according to is the number of hours starting from the moment at which the lamps are turned on until the designing hour which we designed this HVAC system at. So we can suppose that the lamps to be turned on at 8 AM and the designing hour is 4 PM as usual, so the number of hours for this first factor will be 8 hours, so we enter the required column from this row according to the number of hours we have got to be 8 hours. After that, the second factor we need to calculate the CLF according to is the total number of hours that the luminaires will be turned on at which, so we can suppose that our luminaire system will be turned on at 8 AM and they will turn it off at 6 PM. So we enter this column to get the required row by selecting the number of hours to be 10. Now the final factor we detect the CLF according to is the zone type, and this zone type, as we learned it before, depends on the nature of the building itself. So if our building is a single story building, we enter this table to select the zone type. And if the floor is the first floor of a multi-story building, we select the zone type from this table. And also if our floor is the middle floor of a multi-story building, we select the zone type from this table. And if our floor is the top floor of a multi-story building, we enter this table to get the zone type. But for us now, we can suppose that the floor that this printer room is the middle floor of a multi-story building. Hence, we enter this table and we can suppose our building to have 3 free walls subjected directly to the sunlights, and the ceiling of this floor is having a false ceiling, and also the floor is covered by a vinyl flooring, and the partition is of the gypsum board type, and finally the windows of the building are having a full inside shade. So we enter this row according to those information of our building parameters. And now for the column, we enter this lights column as we are getting now the lighting thermal loads. So the intersection between this column and this row gives us a zone type D. Now we are ready to get the CLF value from this table for the lighting thermal loads. So we enter the zone type D main row and we enter the 10 hours row. and we enter the 8 hours column, so the intersection between them gives us a CLF value of 0.87. So by that way we have detected the cooling load factor, and finally we multiply those factors by each other to get the final thermal load of the lighting system to be the total luminaires power of 68 watts times the fraction of in-use watts of 1 times the Pallas factor of 1.1 times the cooling load factor of 0.87. Hence we get a total thermal load of those luminaires in this printer room of 65 watts. More than great. So by that way we have learned how to calculate the lighting thermal loads according to the SI system standard. Hope that's clear right now. Thank you for watching and see you in next tutorials.